Welcome back to Biodegradable Materials. What I'm interested in today is what happens if we have a more traditional, conventional polymer. So in the style that I drew it last time, here is the backbone of a polymer. The hydrogens we can't see, but let's draw one on because we're going to use that one. And what we want to do is molest this polymer in some way. What we know from our experience and what I told you last time, but mostly from our normal experience, is if we take some polymer, some polyethylene for example, and we leave it outside, it eventually gets really hard and starts to sort of crack and get damaged. Eventually it appears to disappear, but we don't think about that too much usually. So there is some kind of process that goes on that causes damage to our polymer. We can imagine it has something to do with oxygen and that it has something to do with light. And what is most likely to be happening is that oxygen is being added, and the weakest bond here would be one of these hydrogens on the side. The carbon-carbon bonds are slightly more difficult to break. So let's take an oxygen. This is O2, and we want to react it with this bond. And one of the easiest ways to do that would be to do the same thing that we'd had before. We could put our, is that going to go that way round? Let's check that it's the right way round. Not that it matters because it's a circular reaction, but effectively our oxygen is going to attack there and this bond is going to go over to here. Let's have it that way round. It's probably nucleophilic, so let's turn it around the other way. It's probably going to be the other way. How's it going to do that? This would attack there. No, let's have it that way. That's better. We've got an H plus instead of an H minus. So we can have these two arrows forming two new bonds. That would be these two new bonds. And the double bond gets broken. Let us resolve that situation. It's got really ugly now. I'm not very happy with how I've said that, but never mind, we've got to go on further. And it was the arrow direction that I originally started with. Oops, I've broken that bond. So let's leave the atoms where they were and move those bonds round. So I'd drawn this one in as a single bond and one to here. That was the bond that used to be to the hydrogen, and so now we can straighten that up to make it more pretty. So we've now got this species in here instead. OH. Let's draw the H on each side. Okay, so we've got a peroxide, OO, with connections to each end as a peroxide. That would be a reactive intermediate, and this can now go on and do things. We know of this species from trying to recycle things like polyethylene terephthalate bottles, where the enemy is this peroxide. It forms mostly during casting, but also with ultraviolet light, and it tends to attack the polymer. Eventually it causes damage and it shortens. Today I'm more interested in this first step. So there is a problem with oxygen. If we take normal oxygen, so those are our oxygen atoms, and we make, let me get rid of some stuff to get some space. Oh, never mind, it will fit. So if we take normal oxygen, we form the S bond, the normal, oops, I've drawn them backwards, but never mind. So we form our normal bond. That would be the single bond between the two oxygens. And then we would like to form a second bond. That would be the double bond. But we discover that it is a little bit weird because we've got a lot of electrons left. And we can form two equivalent double bonds. So that would be, for those of you who don't know, if we start off with a single bond in the middle, that would be two orbitals that interact. That would be this one, and they're interacting to form this here. If we have an orbital on the top, so that would be an orbital that typically starts off looking like this, and an orbital that typically starts off looking like this. If we add those together to form a bond, that would be this one here, and that would form a bond, but it would also form an antibonding orbital. So if we add two orbitals together, sorry, not bonds, if we add two orbitals together, we have to get two orbitals back, and that forms, oh, that's weird, because of the crosses, but it forms a bonding orbital where the electrons are between the two atoms, and it forms an antibonding orbital where the electrons are away from the two atoms. That's this one, I'll colour that one in so that it's obvious. So if the electrons are here, they're holding the two oxygens together, and if they're out here, they're holding the two oxygens apart. These are my two oxygens. This is a different diagram, it's just energy level, but we haven't got the geometry. Because we've got the one in the middle, that would be one pointing in this direction. We've got the ones up and down, but we've got another dimension because we're in 3 dimensions, we're in our normal reality. There's one in this plane as well. So first of all, a double bond doesn't look like how we draw it, an equal sign. It's really a triple sign. The single bond is in the middle and the double bond is on both sides. The oxygen double bond is special because it doesn't have a reason to be this one. It could be the other one as well. So we've got these two possibilities, and we've got the antibonding orbitals, which could also hold electrons. If we put electrons in those, that makes our bonding weaker. If we put electrons in these, it makes our bonding stronger. But we have 5 electrons left over, so that means we've got 1, 2, 3, 4, no, 6, sorry, 6 electrons left over. So we've got our single bond down here, we've got 2 more bonds up here, and now we've got a problem. We've got too many electrons, and normally there's one in each of these orbitals. They don't pair up, they sit in one in each orbital. That's the lowest energy state for 2 electrons in 2 orbitals. They don't go into one orbital, that's higher in energy, and they don't go opposite spin, opposite directions in 2 orbitals. That's also slightly higher in energy. That tells us something about oxygen. It tells us that it should be magnetic. It should be affected by a magnetic field because it's got 2 electrons that are in the same spin. Spin being the property that causes magnetism. And we have discovered a new thing, that we've actually got 3 bonds. There are actually 3 bonds and an oxygen double bond and an anti-bond, a negative bond, which gives us a double bond, which is good because it should add up to our other model. But it also tells us something new. The something new is that our drawing can't possibly work from this oxygen. So what drawing did we have? We had an oxygen. Let's redraw it. So let's have our hydrogen here and our oxygen here. We had an oxygen that donated a double bond, or a bond, into an oxygen hydrogen. That forms this, which I've not quite rubbed off here. Let's move it slightly. Let's move it back up to here. So just bend it round so that it's not interfering with this oxygen molecule here. So that was my first step. It's actually a single step reaction. In this case, if I want to draw it as a cyclic reaction, we don't have to draw it as a cyclic reaction. We could take the proton off first. We can attack the carbon first. It depends a lot on conditions. What really happens, a 4-membered ring cyclic reaction is comparatively difficult to do, but I like it because it's pretty. The problem that we have is that our 2 electrons in the highest occupied molecular orbital, which for teenagers is humorously named the HOMO, that those are the 2 that should attack. If I'm going to drop electrons into my oxygen, they should go in here. And if I'm going to take electrons out of my oxygen, they should come out of the highest occupied molecular orbital. In this particular case, it's the same one. this is where electrons are going to go, and this is where I'm going to get my electrons from, so that's where this process is going to happen. The problem is, I can't get two electrons in there from our bond, because that would be an up and a down electron, because they're in the same bond. And I can't put them into this new orbital between the oxygen and the hydrogen into a new bond, because they would also have to be up and down to do that, and they're not, they're both in the same direction. So my oxygen is quantum mechanically not allowed to do this reaction. That is a problem, or at least it's a hindrance for the reaction to happen. And so what we would have to do before we start the reaction is flip one of the electrons over. We can do that in a variety of ways. It is quite difficult to do with light, because it's quantum mechanically not allowed to flip over an electron. We know that from physical chemistry, those of us that did physical chemistry with me. So we can't just flip one of the electrons by hitting it with a photon of light. It wouldn't take very much energy, but because it's quantum mechanically not allowed, we're not allowed to do it, so it's very, very rare. What we can do is interact with an orbital on a bigger molecule and flip it over. So if we manage to do that, we can flip one of these over. We can also excite it and let it come back down again. And so typically we would have some other process that's making our oxygen more reactive. It's an interesting feature of oxygen that its normal state is actually far less reactive than it should be, just because the two electrons in the highest occupied state are pointing in the same direction, and also the two holes in the highest occupied state are also pointing in the same direction as the other one, but they're in the same direction as each other, and that makes it way less reactive to most things. It also means we can much more easily get one electron out of oxygen than we can from most things. Most things give us two. So if we take our electron and flip it over and shove it into the other orbital, we can make a different type of oxygen, which looks exactly the same. It has a double bond. It's slightly higher in energy, but it is way, way, way more reactive. This is called singlet oxygen. It's called singlet because it's not affected by a magnetic field. So it's a history of names thing. If we have them pointing in the same direction, then we will get different types of oxygen. Some of it will align with the magnetic field, some of it will align against, and then it's called triplet, because there are actually three possibilities in that case. And in this particular case, it's singlet because it doesn't care what direction the field is, so there's only one type of oxygen, even in a magnetic field. Our singlet oxygen is the enemy if we don't want our polymer to degrade. If we don't want to get old, this is the enemy that causes people to get old. When we make our energy inside our body, when we eat food and convert it into energy, we accidentally make this species inside our body, and it is very bad. It causes our polymers to degrade, and that causes us to get old effectively. So skin wrinkling, all kinds of things related to aging are caused by polymer degradation by this inside us. We're going to investigate how it affects a conventional polymer, and the first step of that is adding to the polymer to make this peroxide group. Then I'm going to rub all these things off now, and we will go on from there. Okay, so stage 2 of our reaction is going to be what happens to this peroxide next, and the simplest to draw way of doing it would be breaking this bond to give one electron to each oxygen. That is a special case. So it's a special case because we're forming a radical, and those of you in biomaterials will have done this from another course, polymers. So you will have had something like benzoyl peroxide. It looks like this. Oh, probably, or some similar chemical. You heat it up, it does this reaction. It forms 2 radicals. So let's take that off and just have one. We get 2 of these. It's identical, it's symmetrical, so it forms 2, just the same. And they go on and do the polymerization in that case. What we're interested in here is depolymerization, which takes place exactly the same. So this is now going to make two species. Let's make those. So that would give us this, and they're denoted here by a dot plus OH dot, and they're not charged at the moment. So we've got two things. We've got a hydroxy radical and an oxygen radical on our polymer, and those are now superreactive. What do we know about these radicals? Let's look at the polymerization once more to see what happens, and then we should probably slow down. So let me just put it down to that, and let's look at the radical polymerization. So we've got our radical from oxygen, remembering that we've got one-armed arrows because we've got one electron moving now, not a two-armed arrow, which is what we actually imagine usually happens. This is a special type of reaction. And let's make polyethylene, because then we don't have to worry about too many other things going on. So we would effectively take our radical and we would put it into a bond and steal an electron out of this double bond here. Let's resolve that straight away so that I don't have to draw it all. That gives us this, but we haven't destroyed the double bond, we haven't destroyed the radical, sorry. We destroyed the double bond. We haven't destroyed the radical. We took one electron out of the double bond to make the single bond. We took an electron off the oxygen, and our dot ends up on the end here, and it can continue to do the same thing. So let's draw a couple more of these. So this dot goes in here, this single bond, the second bond of the double bond breaks. One of the electrons goes into here, one of the electrons goes into here. This one, I'll take that one. And that ends up with polyethylene, with a cap on the end, which is this benzoyl ether. So let's rub out all these bonds that we broke. Oh, that's the wrong one. So if we rub out all the bonds that we broke and put in the new bonds that we made, we end up with this. What those of you from biomaterials will have known, will have studied in polymer chemistry, is that this radical can then hit another one and they annihilate each other by one electron from one going in and one electron from the other, and they effectively form a new bond, but there is no radical. That's a good way of getting rid of a radical. Typically this happens in a normal case when our radicals hit a surface, because then they can interact more easily with each other. So what we can imagine is that these radicals have a very high energy and they're quite difficult to get to. The specific case of the benzoyl peroxide is a very stable molecule that you have to heat up and you end up with a radical, but this is a more stable molecule and it is quite difficult to cause this to happen, this breaking. It does happen at room temperature, but it takes a really long time. So what it means is that our PET, even though we've made these peroxide groups, I've broken it, but even though we've made peroxide groups in it, it doesn't turn into rubbish, it doesn't degrade on its own over a short period. It takes several recycling cycles. So here in Germany, you take your PET bottle, you drink your Coca-Cola, you take it back to the shop, it gets shredded, it gets cast into a new bottle, lots of cycles go on. It does build up damage, but it takes a long time, a lot of cycles. So these peroxy groups are quite stable. This is the slowest step in our reaction, and so it determines how fast things degrade with oxygen. What I wanted to mention at this point is fire. So if we take something like methane is the easiest. If we take something like methane, so that would be our methane. Problem with drawing it in this style is we just have a dot. So I have to draw the carbon hydrogens on. And we have oxygen. So we've got our O2. Set on a bit, yeah. Then we can heat it up. And when we heat it up, we end up with new species. And typically what we're going to do here is break a hydrogen off this methane. So this step would be the slowest step. Once we get to a radical, so now we have CH3 dot plus H dot. And let's take the simple one, let's have this plus H dot. So now our hydrogen radical can attack our oxygen and make a new species that will go to, it's going to break our double bond, so it's going to go to OH, it's not straight, but it makes a peroxy radical, because the radical is still on there. It comes from here, so the dot is now on this oxygen. So we ended up with a new radical, and that is exactly why fire continues. So the chemical reason why fire continues is we generate these radicals. They all have no reason to stop. Once they react with each other, they generate heat, and the heat heats up more, and that can cause more to break. So we need to get the heat out of the system, or we need to get one of the two elements out of the system to stop it being able to generate more heat and generate more radicals, or we can suck the radicals out of the system, which is the other explanation of why we can put a grid inside a fire and stop the flames. Because we are doing two things really. We're taking the heat out of the system, so we're not allowing any new radicals to form, and we are also, because we put surface and because it's a metal and the metals can take electrons, we are soaking up the radicals. So if we put a fine mesh inside a flame, we can use it to cut the flame in half. You can either light whatever it is, so we could have methane, we can light the methane below, so between our pipe and the gauze, the mesh, or we can light it on the other side and it doesn't travel through because neither the radicals nor the heat can get through very easily, and so we stop the reaction. So that is good for today. So we've got a thing. Obviously, we can see that if we heat up our polymer, then we end up with a problem, because if we generate any radicals at all in our reaction, we will cause peroxides to form. That's obviously a bad thing if we don't want it to degrade. So if we're imagining that we're going to recycle it forever, it's a problem. If we do want it to degrade, it's a good thing, but we want to control that process very strongly. So we'll look into this a little bit next time.